Right, ladies and gentlemen, all the way from a local grammar school, I'd like to introduce you to Tal Lesham, who's going to mess with your reality.
So first of all, I just want to say thank you for Gary for inviting me here. I've never really done anything, well, no, actually, I've done one thing like that. It was a much smaller group. Let me tell you a little bit about me, a little bit of introduction before I get on to this presentation. So, my name is Tal. I'm a physics teacher in where Gary works, the same school. I would like to call myself also an amateur physicist. You know, I'm not a physicist. I think to be a physicist, you really have to have a PhD and do research, and I don't do that. But I did a physics degree, and after that, I always find it interesting, and so I kept on reading. And I've learned things like general relativity, quantum electrodynamics. But yeah, I'm not a professional physicist. Now, what do I want to say? Yeah. Why did I do that? I really like physics. I want to learn more and more. And what I found, I was getting it becomes a bit more difficult as you learn more and more. You know, they say like the more you know, the more you understand that you know nothing really. And I can't draw anything. But if you imagine, if I could draw like, if let's say, well, let's say like that. This is pretty much me and what I know, all the water that I know. Yeah? And as time went on, I filled up more water and more water and water. But then I realized how much there's out there, yeah? And how little I know. So how much I'm ignorant, really. And it becomes even more, it's more difficult than that, because as you learn more and more and more, then the boundaries between what we as humanity know and what we don't know become a bit blurry. So if this is really like what I know, and let's say the room is what humanity knows, then as we get closer to the edge, it's not really kind of a solid line. There's a lot of like mud you have to go through and things that we kind of maybe know a little bit and not know much. Okay? So when you learn theories like general relativity and quantum electrodynamics, these are really established theories. And because of that, everyone kind of agrees on the main principles there. So the books that are written about them are really clear. So I could just read it. Even if I didn't have a teacher, I could read it and I understood it. When you try and go into things that we don't exactly all agree on, it's very difficult to get books, and most of the books are not very clear because the theories are not clear. So it's a losing battle, really. But something changed about 3 months ago, and I came across this something in quantum mechanics, which I knew I know in this kind of simple thing, and I realized how I didn't understand that. And how not just I didn't understand, how all the physics community doesn't understand it. So if, let's say, this is me, and really this is the boundary of the known physicist, really, if there's actually here, just here, the edge of the glass, is a boundary of what physicists know as well. So I came across this barrier, which is completely solid. It's not like a murky, grayish area. Physicists don't understand that. And by the end of this hour or so, I think you will be able to get to that point as well. Realize this is a big problem in physics. Okay? There's not much maths. There's no maths at all, really. You know, it is a little bit mind kind of expanding, but I think everyone can really understand that. So I'm quite excited about that. I had a few weeks where I didn't really sleep well because it was just, wow, you know, there's this really problem that I understand. I'm in the same level, really, as a top physicist. And that's about that. Also, I think to add to that, it's important to know that most of the big majority of physicists who deal with this area, most of them just don't even see it as a problem, or if they see it as a problem, they don't deal with it, they refuse to deal with it. And there's only a very small minority that think that there is a problem, and they come up with some crazy ideas to try and solve it. Okay? And you can judge later, see what you think. So maybe just like to see kind of, raise your hand if you ever heard of the double slit experiment. Just heard, okay. And if you want to, let's say, leave your hands up if you've done some kind of course in quantum mechanics, some kind of course. So there's still a few. Okay, so hopefully we're all going to learn from that. So if we can go to the first slide. Yeah, we can learn about the double slit experiment and what it tells us about it. Okay. Now, the double slit experiment really is something that, well, people, I mean, we do it in A-level physics. So if you do A-level physics, you'll do a double slit experiment for light, okay? But in the 1920s, they did the same experiment for electrons and other quantum particles, and that is the problem. And that problem, since the 20s, has not gone away. Okay? It's still a big problem. Basically, if you, let's say you have two slits, and you shoot a bunch of marbles, or little balls, shoot them, you can imagine on the other side, if you have like a target sheet, okay, you'll get something like that. You're going to a batch of marbles here, a batch of marbles there, maybe a few here, but majority behind these two slits. If you do it with light, or if you do any kind of wave, and in physics we learn, in high school we learn that light is a wave, okay? You can do it with water waves, you get a very different picture. You get what we call an interference pattern. Now, instead of me talking about that, maybe we're going to show this little clip. Will really explain it well.
And here we are, the granddaddy of all quantum weirdness, the infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now, there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. Physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. It was here that physicists stepped forever into the strange never-world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
So maybe I can just say now that instead of just like if you've got questions and stuff, don't just leave it till the end. If you want to ask something, just raise your hand and answer. Okay, because you need to ask them what you don't understand. So hopefully that was kind of helpful. I gotta tell you, I came across this when you do that probably in your first or maybe second year university, and you learn about double slit and this thing that when you're not looking at find out which slit did the electron go through, and you'll get this pattern. Okay, but when you are looking, some you get that. And what does that mean? How does the electron know? Okay, well, the way I understood it, I didn't think it was a problem because look, you can't just look at electrons. You can't just put your eye here and see where it doesn't work like that. They're too small. You can't even see them with a microscope. What you really got to do is bombard it with light, with photons. Okay, you bombard with light, and so you shine some light, and whenever the electrons went through, collided with some kind of photon, or maybe with another kind of material, maybe you put some kind of material here, wherever you got a spark, then you know that the electrons went through here. Does that make sense? But then, if you put something in the way of the electron, so you can see which way they went through, then obviously you interfere with it. You're going to change the pattern. So that's how I saw it in the first year of university. This is not a problem, If you put something in the way, it's going to behave in one way because you moved it. If you're not going to put anything on the way, it's going to behave in another. I didn't see that's a problem, okay? But it is a problem, okay? For many years, some physicists, not many, tried to come up with a similar experiment, but one that will remove this kind of loophole, this way out of saying what, like I said, something to get away, not to observe which slit the electron went through without actually interfering with it. And they managed to do that, okay? They did two experiments, one in the 80s and one in the 90s, okay? I'm going to talk about the one they did in the 80s, okay? So if we'll go to the next slide. Right, it's called Quantum Eraser Experiment, which is really, really quite an interesting name. And I was not aware of it until 3 months ago. And maybe actually you might be interested later on Googling. I came across that through an email I got from my mum, who gave me this guy's name called Tom Campbell. I don't know if you've heard of him, Tom Campbell. A bit of a, he's got some interesting ideas there, way out there. But he talks about that. So, you can have a look at him later. You might like it. It's some interesting ideas. Some of, it's not my sort of stuff, but that's his kind of basic thing of his theory. Call it my big toe theory of everything. Okay? Yeah, and what he basically said, he said they did this experiment, this double slit experiment. They did, let's say, 100 times. And they saved, they saved the data, which slit the electron go through. They saved that data in the computer. They didn't look at the data. They just saved in the computer. And they also didn't look at the screen. They just saved that data in, let's say, another computer. And they did this 100 experiment. They saved the computers and they left it for a year. And then the year after they came, and they took 50 of the computers, in 50 times of the experiments, 50 experiments, they took the computer that stored which slit went through, and they just smashed it. And the other 50 experiments, they left the computer all right. Okay? Now they start looking at the screen. So they found that wherever they didn't smash the computers, in other words, where we knew which slit they got their electron went through, what they got on the screen is that. And where they smashed the computers, okay, so we couldn't really tell anymore which slit the electron went through, they got that. And when he said that, I said, this is nonsense, this is silly. I was going to say, no, this guy's crazy. But he was right, okay? Effectively, that's what they did in this experiment. Maybe not as dramatic as what the way I said, but effectively they did the same thing. That's the eraser thing. They erase the information. And what I'm going to try and explain it. Hopefully you'll get it. It's not a bit complicated. So to do this, what you're going to do is do something called entanglement, okay, which you might have heard as well. Okay, I just heard of it. I don't know too much about it, but basically it's possible to take a particle. In this case, they work with photon. Right? Take a photon is a particle of light. Okay, so they take a particle and they turn it into two particles, like two twins. That together, their energy will be equal to the energy of the original particles. You can imagine like a parent particle, okay, give birth to two little particles that all together have the same amount of energy, but some of their properties you can really predict. From knowing one, you can predict the other. So for example, and again, why, never mind, I don't know that, so I'll be honest with you, but if I need to explain to you what polarization is, so maybe I'll explain that first. So photons light have this property called polarization, and it's not difficult to understand. You know that light, you used to think that it's a wave, and a wave can, let's say, move like that, or it can move like that. Okay? So we'll call that vertical polarization, or Y polarization, like the Y axis, and this will be a horizontal polarization, X polarization. Okay? So it turns out that if you create these two photons, which we'll call P and S, if P is a Y or vertical polarization, then you know with a certainty that photon S, the twin brother, is going to be an X polarization. Okay? Why? I don't know. Never mind. We'll just believe it. Okay? All right. And if this is X, then that is Y. We know for certainty. Even if this one is, we send them to one side of the universe and we check and we know it's Y, this one is on the other side of the universe, we know straight away it's an X. Okay. Now, what we do, we send them these two photons in different directions. Photon P goes to a detector. Okay? And by looking at the photon here, by finding out what's his polarization, we then know what polarization is. And that's the whole purpose of using P. Photon P. That's the whole purpose, okay? We call him an idle photon. We're not doing the experiment with him. He's just to give us information about it. Okay. Our photon S, he's the one who actually goes through the double slit. You can see there's a double slit here. So he's the one who will do the experiment. But before we let him go through a double slit, we have to pass him through this something, which is called some kind of crystal. I don't really know how it works, but what that crystal does, he messes around with his polarization state. Okay? Changes it. So, for example, I did say that there's a Y and an X. If you take a Y and X and combine them together, you can get some kind of polarization state like that. Okay? It doesn't matter if you understand why, but this doesn't matter really. So you can take, you can make a photon, you have a polarization like that, which is, I'll have a look like you guys, it's a anticlockwise, yeah? Anticlockwise we'll call a left polarization, or you can turn it, you can make it turn clockwise, and then we'll call it right. Okay? Now, this crystal, we've got actually two crystals, one in front of each slit. So this QWP1, this crystal, takes a Y polarization and turn it into a right, or a clockwise polarization. Okay? Right? It will take, if that polarization state we start with was X polarization, horizontal, it will turn into anticlockwise. Okay? The one here in front of the second slit does exactly the opposite. So if it will take a vertical polarization state and turn into anticlockwise, just the opposite of the one from slit 1, and it will take an X and turn it into a right, so clockwise. So if you kind of hopefully can see that if I knew what was the polarization state before I got into the crystal, And if I measure what the polarization state I get here, I can tell which slit it went through. For example, if I know, I measured here and I know that he's in X polarization state, then I know for certain that he was Y. Okay? Now let's say I measure right polarization state here in the detector, then I know he went through slit 1. If I measure the left polarization or anti-clockwise, I know he went through slit 2. If I measured this one to be Y polarization, then it's exactly the opposite. That's the hardest bit, really. That's the hardest bit. From now on, it becomes more easy. Okay. So, what is the system here? The system is that I can tell, create a system where I know which slit the photon went through. And if I do that, I do get this pattern. Okay, just like before, I knew effectively, I don't really see any sparks here, but by measuring the polarization state, I can tell exactly with certainty which slit it went through. So I get that. Now, again, if you like me, first thing that I read that, I said, well, that's again, it's not a big problem because I put something on the side, on the path of the photon, so I'm interfering with it. Of course I'm going to get a different pattern. I'm going to get interference. But then, they told me, I didn't do it, I had to believe them, but they did this experiment without entangling, without these twin brothers. They just sent light, normal light through it. Bunch of photons. And they didn't get that. They got that. Okay? So it's not the crystals that change their path. It's the knowledge. It's our knowledge, okay? Our measurement, our knowledge that we know which slit they went through. When you send a bunch of photons and you don't know the polarization state to begin with, because light is normally not polarized, then you will get that. When you do, we know the polarization state before and after, and then you can figure out which state it went through, you get that. So that's a bit weird, okay? It gets weirder, okay? So what they did now, they've got in a system where we know where the slit is. Now we want to destroy, we want to erase the knowledge. Just like Tom Campbell was talking about smashing the computer. That's where the eraser comes from. So what they did, they've put a polarizer. A polarizer is basically like sunglasses, you know. That takes, it allows only one direction of polarization to go through. Okay? Now, if let's say I've got a Y particle, a Y polarization state, and I pass it through a polarizer that looks like that, I'm just kind of thinking about it like that, it doesn't really look like that, it will let it go past. But if I turn it around, and I've got a vertical polarization, it won't be able to go through, so nothing will come through. Okay? If I turn it like halfway, and I've got a Y polarized state, it will let some of it go through. It will reduce the amount of light that goes through, and that's what shades do. Okay? But what it will do, it will change the polarization state. Whatever comes through is not going to be Y vertical polarization, it will be something like that, diagonal. Okay? Now a diagonal polarization state is really made out of two polarization states, a little bit of vertical and a bit of horizontal. If you've done anything with vectors, that makes sense. But even with arc, okay, if you've got a straight line like that, a diagonal, and that's the polarization state, well, it's a little bit of that and a little bit of that. So if I put a polarizer like that diagonally, and initially I have a Y polarized state, I've changed it. I've changed from just purely vertical to a mix of vertical and horizontal. So now when we get to the detector, we don't know for sure. We won't be able to measure. Some of it will be X and will be Y. We'll never know exactly what it is. There's a bit of uncertainty. Now if this is a bit of X and a bit of Y, that is also a bit of an X and a bit of Y. He's not pure anymore. And if he's not pure anymore, okay, then we don't know what it was before, okay? We will not know which slit he went through. Because to know which slit he went through, we need to know if he was X or Y. That's the eraser, okay? And if you're following me by now, you won't be surprised to know that as soon as we put the polarizer, okay, that means as soon as we don't know which slit it went through, it reverted from here to that. Instantly, straight away. We erase the information, okay, and the photons decided to behave differently. Now, this is quite shocking, I find it, because, you know, it's not that you know, in the experiment before, like in the YouTube you watched, they had a little eye there, like some kind of measuring system. So you were changing whatever you've done here. Here they didn't touch that. They messed around here. They changed what they've done here. So by deciding to put a polarizer or not putting a polarizer, it created the effect here. This is what physicists will call a non-local effect. Meaning I'm doing something here, and Gary's hair goes on fire instantaneously. Yeah? I'm creating a non-local effect. Physicists don't like that. Einstein hated that. He called it he called it spooky action in a distance. And actually, I've got, in German it has a specific name. I don't know, Spuken something like that. I read it somewhere and it was really nice. But it has, because it obviously spoke German.
I know the term, I can't remember it.
Yeah, I've got it in another PowerPoint I'll later read. I've recently just read, because I think he pretty much made up this term, spooky action at a distance. You know, what's happening here, okay? The photon goes in, right? It hits the detector, and he says, right, they're on to me. They know what sort of photon I am. So what does he do? Okay, that's what physicists basically are saying. Okay? They're saying, he sends him a message, the photonist, he said, look, they know who I am, that means they know who you are, that means they know which slit you're going through, that means you gotta behave like that. Okay, these are the rules. Now, as soon as I put a polarizer, he sends him a message that, look, don't worry about it, they don't know who I am anymore, okay? You can go and behave like we normally do, okay? Right? Spooky action at a distance, yeah? Now, physicists forever trying to figure out how it works, they never really get into like, why are they doing it? Why are these photons messing with our minds? You know, why are they doing it? That's, physicists don't deal with that. But it gets even crazier, okay? Now, in this experiment, to be honest, that was the age. They didn't go further. But they have another experiment. If you just skip on to the next one, which I'm not going to talk about. This is a little complicated. I'm not going to talk about that. But they did that in the 90s, these guys, okay? But if you go back to the first one, what I will do, I'm going to lie a little bit. And I'm going to stay in this frame, in this system, but I will tell you what was the conclusion based on the more complicated experiment. Okay? So what they did, okay, they took this detector further back, okay, to make sure the photon P hit the detector after photon S hit the screen. Okay? And they decide, you know, they messed around. Sometimes they put the polarizer, sometimes they didn't. Okay? And even though photon P hits the polarizer or the detector well after photon S hit the screen, it was still the same thing. And the conclusion, you can't escape from it. This is what, again, physicists call retrocausality. So things in the future affect the past.
Could you set up your system so that you analyse the pattern and then put in or don't put in the filter the other way around? So
Look at the
when it
results
came out,
first and then.
break the universe so it shouldn't be
I gotta think about that. Say it again. Because I thought I knew what you were going to say.
If you've got your filter in, your polarizer in,
Yeah.
you get one pattern as opposed to the other.
Yeah.
If you could move your detector and your polarizer sufficiently far
Yeah.
that way, so your electrons come down here, produce their pattern, you can analyse the pattern and go, oh, they're behaving that way.
And then change.
I will or I won't put the polarizer in
Yeah.
to produce the other pattern.
Yeah.
Light to get
Well, but it's not, you won't do it as far as the spirit, but in theory, if you put it on the other side of the universe, it might take them another 1,000,000 years until they reach us. So again, I think this is definitely valid, as far as I understand. I got to tell you, after this lecture that I did in our school, 2 weeks after, a kid, you know, Gary knows the story, a kid who was actually not the best in physics, but he's really good in computers, and he came to me and he said, look, can't, and after that, I thought what you were going to say, he said, can't we use that to predict lottery numbers? And to be honest, looking at the way he's done it, I'm like, maybe yes. Either I don't understand that, or maybe there's some kind of thing that I don't see, but it does work. The retrocausality, the future affecting the past, if that is true, then yes, these things are possible. Let me just almost finish, because I just want to say one thing that, just to kind of force that point, because I'm not sure everyone got it. If this is sufficiently further back, then the photon hits the polarizer or not, okay, has to send a message back to this photon S to tell him how to behave. So this, photon S hit the screen before the photon P hit. So he doesn't just have to catch him, he has to go back in time. Okay? And I can tell you there's a bunch of people, Yakira Aronov, he's the lead guy of these school of thought, and they do say that. They're clear about it. The future does affect the past. I'm going to show you another way of solving it without messing around with time. Yeah?
Yeah, but the thing with lottery numbers, isn't it the fact that the rules of quantum physics don't affect the macro world, so you couldn't actually use it to predict lottery numbers because they're macro?
It's a macro thing. Yeah, there's truth in that, and I think a lot of physicists will say that. Well, this is a macro world. It's photon behaves here, but the picture here, there is a macro world. So I'm not disagreeing with you.
I think that the whole tricky action at a distance thing is because theoretically the laws of physics are somewhat different.
If you're not truly predicting the lottery balls, what you're doing is you're taking the information as to what they actually were and sending it back to before they were, as opposed to working out what they're going to be.
Yeah, I'll tell you.
The show does that affect the results?
Yeah, I'll tell you his idea. He basically says, I didn't think about it, he thought about it. So he said, well, yeah, you move that further back, and what you do is let's just make it simple, okay? So let's say we've got a box, okay? And in the box, either there's a silver coin or not. Okay? And he said, what you've got to do is, you send these two photons on their little way, just like that, okay? And you send them, let's say, on, 1 o'clock, and then you open, okay? Oh, sorry, before you open, okay? So photon S hits the target, hits the screen, photon P carries on, yeah? And then you open the box, and you see if there's a silver coin or not. If there is a silver coin, on the path of photon P, you put a polarizer. If there is not, you don't put a polarizer, okay? The theory is that whatever happened after you open the box will affect what the photon S did when it hits the screen before you open the box. So you still have to open the box, but you will know what you saw there before you opened it. Doesn't make sense to me. I don't know. There is one complication here, though. There is a big complication, in fact, is that we're not talking about just one photon. We have to send probably, I guess, billions of photons to get this pattern. Okay? And so there's plenty of complication here, but the idea, the theory that the future affects the past just comes out of these experiments. Well, there's one way to kind of distinguish that, get rid of that future affects the past, and I'll show you that in a second. There was a question there.
I've got two, actually. I'll do the serious one first. Even with the basic experiment where the two detectors are equidistant, doesn't that mean that the message passed between photon P and photon S has to be faster than the speed of light?
Absolutely, spooky action and distance, yes, absolutely.
So information travels faster than the speed of light,
yes,
even if we can't.
Yeah.
And the second thing is that if it's a shame that Camelot never used quantum-sized lottery balls. We're seeing as retrocausality is in effect, can we all will them to use quantum-sized lottery balls back in the 1990s when they started? So
you will send the message back.
Yes.
Yes, but then there'd be lots of really rich physicists around.
How do you think they funded that collide? But would the knowledge of knowing there are lots of really rich physicists mean we know they sent the message back and that would break the quantum multi?
So if there's no more question, there will be time some more. Let's move on to possibilities of solving that. One more? Right. So again, like I gotta tell you, like I said in the beginning, that most physicists who deal with these fields, they'll say this is not a problem. They'll come up, either most of them, and I read that from some physics paper, a really good guy said, most of them just completely ignore it. Completely ignore it. Don't talk about it. And don't mention it. And there's a reason. If any one of you have some kind of, understanding of academic world, you have experience, like anything in life, it's a lot of politics. Okay? And these guys have to make a living, like all of us, and like most of us anyway. And to make a living, you have to write papers, and you have to get grants, and you have to, now this is a problem, it's in the 20s, there's no solution to it. So why, if you like a young PhD, just got your PhD, trying to get tenureship. Why would you try and meddle with this thing? There's no really money in it. Okay, and the conclusion, I'm completely insane. Who's going to give me grants? So instead, they're trying to find the Higgs boson, who, being speculated about in the 60s. Everyone agrees with that, and that's where the money is, Not real money, there's even more other fields. But so most physicists will just not deal with that, completely ignore it. Some of it will say, yeah, there's a bit of a problem, and they come up with these crazy ideas like the future affect the past and other ideas. These guys, I don't know too much about them. It's called digital physics. It's a non-mainstream physics, but it doesn't, it is part of the mainstream, but very, very little. Okay? I know there's some Oxford professors working with that. He's the most famous one, Wheeler. I knew him just because I learned general relativity from this book. It's really big. He works at Princeton. He's not alive anymore. He worked in Princeton with Einstein. So he's like the one major guy in digital physics. And he coined this thing called it from bit. And that's what makes the computer guys really like. He basically, these guys, and there's different kind of levels in their interpretation, but some of them say that the universe can be explained as some kind of simulation of a computer. To the ones that are really fanatics who say the universe and everything in us is a computer game. So we are actually in a computer game. These are the real hardcore kind of digital physicists. It from bits, it means that basically that every physical object thing in our universe is really a bit from a computer, some kind of computer game somebody's running, I don't know.
Yeah, Marcus Shan, I think, explained that in, I think it's Another 11 Days of Being Dead, where he says that the possibility of you actually being in the simulated reality is greater than the possibility of you actually being here.
Yeah.
Very good book.
Yeah. I'm new to this. I've never heard of it. I think it's insane, but I think in that experiment it convinced me, and I'll try and show you. So let's move on to the next one. This is what I think most of us. Well, I don't know about you. That's the way I perceive reality until recently. Okay. So I thought, like they say, what sound does a tree make when nobody's there in the forest? I think, well, a tree's there. A tree's there. It makes a sound. Maybe no animals heard it. Okay? If you put a recording device, you might hear it. But even without, the air vibrated. There was some kind of frequency. It's there. It's real. And I'm not looking at you. Okay? You guys are still there, right?
No, we don't.
Okay? So that's physical reality, which I think, even if we don't all, if some of us maybe think there's something beyond that, this is the mode we function. Even maybe if you think that there is some kind of, aliens or some kind of, or hidden realities, day to day, that's how we live, right? Hey, we put the toaster, bread in the toaster, we go back, just, we don't just live like that. But maybe I'll show you the next bit. And this, people who play a lot of games, they think of the reality like that. And I'm going to have to take over here because I'm going to stand there now. Mess around a bit. Now, in a virtual reality, in a computer, things are different, isn't it? When I'll just come in a minute. If I want to think about, I tell the kids, if you've got, let's say, you're playing some of these computer games, the kids love it, and they play something, let's say level 5 is a monster, a really nasty monster like that, okay? And you just start, you turn it on, and you're fighting some other monsters, not as dangerous as this one. And then if I told the kids, do you think that this monster kind of sits there and think, when's he gonna come? Do you think I've got some time just to go get a cup of tea before he comes along? And then he talks. That could be insane, isn't it? Of course he doesn't exist, this is just a virtual reality. He's just, where is he? He exists somewhere in the memory of the computer, right? Even if the computer is switched off, he's still there somewhere in the ones and zeros or whatever that is, these chips, okay? But he doesn't exist really, okay? What happened is, when we turn on the computer, and once we got to level 5, okay, then Tom Campbell used the word renders, okay? Okay, the memory, we've got a little bit of a problem there. Place. I'm going to place. Enable anything. That's it. Cool. All right. All right. So what are we going to do?
That's fine.
Fine. Let's try again. Copy. Here we go. That looks a bit better. Okay. So as soon as we switched on the computer, okay. Soon as, well, really, actually, I should have got rid of that first of all. Soon as I switch off the computer, then out of the memory, okay, this figure is being rendered. That's what Tom Campbell called it. I don't know if you're into computers. Render. It renders it. Okay. Before that, the hero, the you know, what do you call avatar, did not exist. It's just in the memory. But now it goes from the virtual, from the consciousness, from a metadata, it becomes on our screen. So now he becomes real. Okay. And then in level 1, he fights all these people, and then eventually he reaches level 5. Okay. And again, the memory renders this monster. Now he exists. He went from your metadata, from your memory down to the data. Now we can actually see it on the screen. Now he's real. Okay? And then, you know, he goes to level 6 and he killed the monster, and the monster ceased to exist. And he goes to level 6 and, I don't know, in level 6 he just rests, you know? And he rests under a tree. So now the tree exists. But he didn't exist before. Okay? He was just in memory. Okay? So you've got these two notions. In the virtual reality, we've got two things. You've got your metadata and you've got your data, what you see on your screen. Okay? That's your physical reality, and that's what Tom Campbell called consciousness. Okay? And the computer is just a memory, not just consciousness. So these guys basically say that we are living in that kind of reality. And everything we see, everything we feel, we're just making measurements. It's like our screen right now, okay? But it doesn't really exist, okay? When we're not making these measurements, they don't exist. They do exist in some kind of consciousness sphere, okay? Okay, so when I'm not looking at you, well, you're looking at each other, so you still exist. But if nobody's taken a measurement of a certain tree somewhere, then it doesn't exist. Which is a bit insane. Yeah.
Sorry about this. That's a really terrible analogy.
Yeah.
Because those objects do exist, because the code that creates them exists.
Yeah. 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 I
They
agree.
may not be running,
Yeah.
but
Yeah.
they're not instantiated.
Yeah.
But they exist because the code that creates them exists and is permanent.
Yeah. 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 I agree with you.
So
Yeah.
it's not really that it just suddenly.
I'm in complete agreement with that, but I say when they exist as the code, they're here, they're in the metadata. They're not acting. It will be silly of us to think about these monsters when they're inside the code, kind of debating if they've got enough time to make a cup of tea. No, they're just in the code, yeah? They're not really active, isn't it? They're out there, okay?
Yeah.
In that sphere. That's, you got it. I'm agreeing with you.
Of their own and existence.
Yeah. So these guys saying that our world is like that. And I got to say again, this is not mainstream physics. It was a few of the mainstream, but very, very small minority. They say that our world is like that. We've got some kind of code. You call that. I like the word code. I'll use that as well. Consciousness, metadata. Out of this cloud, certain things can be rendered and become real once we make a measurement. Okay? Now I'll go back to the experiment and explain how it works, how it solves that problem. Alright. Alright, so maybe you can take over now. Render the right side. Still drinking his tea. There we go. Okay, one more accent. So, you know, what was the problem here, in my opinion? Okay? There's a spooky action in this. Is the fact that you've got these two photons running around, these real photons running around, and try and find out how they can trick us. Okay, so first of all, why do they want to trick us, really? But secondly, they want to trick us so much that photons from the future can send a message to a photon in the past. And that is insane, okay? But everything is insane, so it could be true. But if we say these photons do not exist, they don't exist. They are some kind of code, okay? If you do quantum mechanics, you call them, there is a wave function. A wave function, again, if you know quantum mechanics, some kind of, is a not real thing. It's just completely purely mathematical, but it helps make the answers correct. So they don't exist, they don't physically exist, okay? When do they become physical? Okay? Two options. One, over here in the screen. If we don't do any measurement in the middle, they will become real here in the screen when we measure them. So they only become real when we measure them. Now if we didn't do all this mess and we just let them go all the way to the screen, or alternatively, if we destroyed this the certainty with the polarizer, so we didn't know which slit they went through, then they only become real on the screen. Okay? And that means overall here, they didn't exist, they were just some kind of code. Okay? They were in the memory, and they became real here. They were rendered here. And they behave according to certain laws of physics, which means they're going to if you use quantum mechanics, that wave function will interfere with each other, eventually collapse here. Okay? They will interfere with each other. If, on the other hand, you've got this setup, where according to this setup you can't tell which slit it went through, then they will become real not here, they will become real at the slits. Because where you made the here, without this, you made the measurement on the screen. In this setup, you made the measurement, effectively you made the measurement in the slits. So now we know which slit they went through. That means they became real. They went from being a code to become real photons here, not there, here. And then, after that, they have to carry on behaving like particles according to the laws of physics. And just like marbles, okay, will not give you an interference pattern, they will give you that. Then these photons who became real here, just like real marbles, they all behave like that. In my opinion, as crazy as it sounds, it makes more sense than things going from the future back to the past. It doesn't mean that this is true, but it's just, it's appealing to me. It's appealing to me. Okay? But I'll just repeat it once again, last time, and then if you've got any questions, is this kind of, I guess, thinking, it's not a theory, it's a thought, that nothing is real until you actually measured it. It exists in some kind of sphere as a code, okay, as consciousness, as metadata, as a memory on a computer. Once anyone measured, by the way, it doesn't have to be me, it could be anyone. Once we create a system where it's being measured, then it will become real. Just like the monster became real. Until then, it's not real, okay? And from that moment that it became real, it will continue to be real and behave according to the laws of physics. Whether it's classical physics, it's macro, or if it's a tiny quantum, if it's micro. Okay? And if you made the measurement here, by this setup, then they became real at the slits, they will continue to behave real, so it will behave like that. If you didn't make these measurements here, and they let them carry on being these waffly kind of mathematical, non-real entities, they all become real here, and they will show you this. Yeah, you want to ask, yeah?
No.
Thank lady in the back, yeah.
Is that not slitism? Is it not?
Is that not?
Is it not a bit slitistic to posit that things are only real when you observe them, or is it a function of observation by everything? So you say true, false, and Paris, it creates a vibration. Are those vibrations therefore the observation of the people in the
Look, as far as there's $1.5 million problems with this. This is insane, isn't it? I'm not preaching to try. I'm just trying to see what you think and you guys. But so yeah, I mean, from what I understand, it's not everyone have to make this observation and then it become real. So if if I'm not looking at you, but you're looking at each other, you're making measurements, then you are real. Okay. So if a tree falls in the forest and there's a little mice that hear the sound. I don't know if there is. The question is, yeah, how far away do you have to go from one human being to say if somebody made a measurement? I don't really know. Yeah.
2 points really. One is deciding where it becomes real according to what happens to the other part. Isn't that just the same as deciding whether to be interfered or go straight through? And if something becomes real,
Yeah.
it obviously starts off at BBO. How does it become not
Right,
real?
very good question. I've got an answer that if you don't mind before you go to the next one because I'll forget.
Sure.
What decides if it's real is very simple, one word, information. Available information. So when you got this set up, then there is an information possible to get which Slit you went through. Right? If you understood this whole business with XY, the information is there. It doesn't matter if the photon hits that before it hits the polarizer or not. The information is there. This thing solves the problem of retrocausality. There is no retrocausality, if you understand what I've said, because when the setup is like that and there's no polarizer, there is an information. Someone can get that information which Slit it went through. And if someone, anyone, even if it's a bacteria, who can read computers, if the information is available, then it's been rendered. When there is no information available because somebody put a polarizer, even if the polarizer is on the other side of the universe, then the information is not there. Just no information. If the information is not there, then it doesn't become real. So things become real when information exists. Information is what in physicists we call a measurement is made. So all these guys who do digital physics, they do is quantum computing, they into information. Information is a very important word for them. You want to ask another one? Or?
Yeah.
Yeah.
Well, the other question was, how does it become not real, or at least BBO?
So when there's no information. When somebody changed the setup, so now the information doesn't exist. If you didn't even touch that, but you put a polarizer there, the information doesn't exist anymore because we don't know, we can't make these measurements.
So does that mean there's a difference between observation and measurement? Because if you had a little mouse sitting at BBO, it could see the two beams of light, but it can't see the results of the experiment, it wouldn't know what it was looking at if it did. But the machines are measuring it, so is the mouse isn't, there's no information what the mouse is looking at, even though it can see the two beams of light, but there is, once it hits the screen, and the physicists can see it.
I'm not so sure I understand, but I would say observing is also collecting information.
So, if you've got someone standing at BBO looking at the light beams, but
Yeah.
not looking at the results,
Yeah.
do they change the...
I would say it will. It's just the reason why we can't. I mean, I would, probably the easiest way of, making what they call a clean experiment, one that will not interfere with photon, is to put our eyes very close and maybe like a mouse. If we had a mouse that could see individual photons, we would just be able to train him to tell us which Slit it went through. That would be the idea, because then we really didn't change anything. But that would be an observation. I would say that was different.
I was thinking more that you see what the diagram where it says BBO and the two light beams on.
This,
you could have someone
yeah.
observing the two light beams,
Yeah.
and they don't know the results of the experiment, but they can see the physical light.
Again, if let's say theoretically we had this hypothetical mouse that could see which Slit he went through.
No, it's not looking
no,
at the slit, it's just seeing that the light beams exist. So
I
it can
see,
it,
I
it
see.
observes the light,
Ah.
but it's not measuring the
I
experiment.
see. So you basically you're saying, let's say we've got these two beam light, but we're not doing anything with that. We're not catching them,
Well,
and we're just focusing.
You might be catching it, but you've got an observer at BBO who's not related to the experiment, and then you've got the experiment.
So we've got observers here and observers here. They're making-
Yeah.
Tal,
Yeah.
it's...
But they're not talking to each other.
But they're not
No, no.
talking to- you've
Yeah.
got- Yeah, and a
Yeah.
third observer at
Yeah.
BBO.
My understanding is that it will, from what I think, it will still behave like I said. The observers, from my understanding, I don't guarantee, but these guys, observer here and observer there, don't necessarily have to talk to each other. The information is available, so they
So
can.
so
But if they don't have to
measurement-
talk to each other, I think it still will behave. You know what I mean?
Yeah, so measurement is different from just raw observation without knowing what you're looking at.
I guess so. But yeah, I think, yeah. I'll just take a few questions from people. You all asked already, so I'll go back to that.
Can I upgrade your mouse to an owl? Because an owl retina is so sensitive it can detect the single photons. Hence, an owl on its own can be the two-slit experiment. in essence, the pattern of electrons or photons on our screen tells us whether we are going to insert our polarizer in the future. And hence gives us the opportunity to, as I say, to break the universe by doing the opposite. But if in fact the universe is completely mechanistic, there is no free will, even atomic decay is not random but just by a set of rules we don't understand yet, then we don't need information to flow from the future to the past because it's just part of one big,
So if you understand all the
three-dimensional,
rules.
four-dimensional painting.
Interesting what you're saying now. I've got another lecture that I do, and maybe I'll do it some other time. And what basically you said is that and I guess that's what your belief is, or some people believe, that if the universe is deterministic, meaning that if you know like the beginning condition of a certain, if I know the height of this glass and the speed that I push it, I can measure very, very accurately what will be the speed after every certain second. That's deterministic. Now, interesting you're saying that. Obviously, quantum mechanics is not deterministic because it only gives us probability. If you've done some courses about, you know that if you've got an electron in a certain position, you know the force applied on that electron. So if, let's say, this is electron has a certain force, quantum mechanics cannot let you predict with certainty where it's going to be after a second. It just gives you probability. So quantum mechanics is not deterministic. But Einstein, and to be honest, I always thought that as well. And I didn't know that was a problem. I always thought that quantum mechanics is a theory which is basically incomplete. Why it's incomplete? Because it doesn't give you 100% prediction. But probably we just don't really know all the variables that affect these things. It's this thought is called hidden variable theory, which Einstein, Podolsky, and Rosen had these guys. They were trying to kind of destroy quantum mechanics with that. They said, well, you just don't know what it is. You know, if you say that the electron is 20% here, 30% there, and 50% there, that just means you don't know. The electron knows where he is. He's here, there, or there. Okay? We might one day have a theory with hidden variables that allows us to be deterministic. Now, it seems like they were wrong. Okay? And this is a topic for another lecture called Bell's inequality. Okay? You might think, how do we know that if there's hidden theories that we don't know about them, or there is no, and it's all chance? And this guy, this very clever guy called Bell, you know, any other names, in the 60s came up with a test to see either our world can be explained by quantum mechanics where there are uncertainties and it's only probabilities and there's never a way to know for sure, or we might one day find out a theory with hidden variables that will be deterministic, that will tell us all these things, including radioactive decay. And they did the test and quantum mechanics won.
Sounds like
But it would
a
have
panel
to
for
be the
next
universe
year.
is set up that way, that quantum mechanics has to look like the answer. That's just how the universe
Deterministic.
So the universe is not deterministic. Oh, unless it's trying to kind
Well,
of...
from the inside it looks like quantum mechanics work.
Yeah.
If you can see it properly from the outside, you
Yeah, possible. Yeah. Yes.
With your idea of having a virtual reality and a physical reality.
It's not my idea. I've got to
Well,
say.
the idea
that
that one you presented us with. Okay.
Yeah.
How personal does that make reality? Because for instance, I don't know how exactly it would pertain to the double slit experiment. When you turn your back on us, and we're still sat there, we could silently move out the room, and you would still think we'd be there, and the waveform would only collapse when you turned round. And I'm sure we've all had an experience, and I had one last night when I was driving down here, and I knew various people from Plymouth from 15 years ago, and I didn't know what they were like now, and only now that I've physically met Gary and Alison and Dave and the rest, I know what they're like now. So does that mean
Your information of us was
has been
15
updated?
years old, and
Yes.
it was, and then that waveform collapsed and the new waveform was created.
Precisely.
When I
So
walked in
does that make the measurement, the perception, and in effect your physical reality personal to you? Because you're the only person who's viewed it. I mean, in the example of the mouse at BBO, because the mouse is looking at the waveform and measuring it. and
We're all in
observing
the
it,
mouse's universe.
then the mouse knows what if the waveforms collapse for the mouse, but not necessarily for the scientist who hasn't actually done the observations yet themselves.
To be fair, I think from what I've read, I think they say, you know, it's not that the world is personal for everyone. From what these people I read, they will say, as long as a measurement, it doesn't even have to have, like, let's say, somebody who did a physics degree or a master's or PhD does the observation. That does not affect, you know. As long as there is a setup that allows potential for anyone to get information, then that will make it real. Well, you know, what's his name? Well, Tom Campbell did say, he was talking about different, you know, and he goes on into some kind of crazy, you know, things that are not exactly my cup of tea, but some of them I do agree. And he says, let's say, you know, I'm like, you know, healthy, you know, all doing well, and I, okay? But let's say, you know, nowadays with, you know, cancer, they talk a lot about doing these tests, you know, these genetic tests. I personally hate that. I think it's awful. And he kind of explained that, and I agree with him. I'm going to say, so let's say, you know, maybe in your family, you've got a lot of people with that disposition, and somebody convinced you to do this genetic test that, you know, what's her name? She even chopped the boob off, you know? What's her name? Julie, no, just because she had the gene, isn't it?
Yeah.
So, you know,
4% chance of breast
yeah.
cancer.
So there's 4%. So let's say you don't know. Let's say you don't know. Okay, I don't know. And now you go and you do the test and say, like, you've got that gene. And they say 40%. Well, that obviously affects your reality, isn't it? That does affect your health. Okay? Well, I mean, I think anyone who's not completely just believes in the medical system, everyone who's got a bit of experience in life knows that whatever you feel here and here affects your health. We know that. Okay? So if you know that you got 40% of getting that, then you know what? You probably have actually 45% now, probably even 60%, because you made that measurement. Okay? If you don't know, well then, you know, you still have 40%. I think you've got less. I personally think you've got less.
Self-fulfilling prophecy.
I think so. I think so.
Yeah.
So,
In all my years in medicine, I've heard of all these, you know, he turned his back to the wall and died, and you hear it, and positive thinking doesn't help, and negative thinking, yeah, people don't look after themselves and commit suicide, but it doesn't make tumours grow faster and slower.
yeah, you don't disagree with that.
No.
Okay.
I have to admit, when Tal told me this, I just thought, that makes me a small man in a shack with a cat that people come to sing to.
Yeah.
Yeah.
It's
you told me
hitchhikers,
about
yeah.
that. You told me about that. I didn't-
This audience got it.
And frankly, Gary, if you made all of us up out of your imagination, you're even more warped than I gave you credit.
I will lend you that book.
If we switch fields, would you believe that believing your experiments work is more likely to make them work? I don't think you would.
If my experiments...
Yeah, if you're in the physics lab,
Yeah.
believing your experiment is going to work, will that make it work? I don't think anybody would
Yeah,
say it does.
no.
So,
Yeah.
over
I'll tell
in
you...
my field, I say I don't believe believing tumours will grow, don't grow.
Sorry. Tal.
I think she was, yeah.
What happens though when reality forces itself upon you? On the 7th of April, 3:30 in the afternoon on the medical ward, I collapsed. 2 months later, I found out I had a brain tumour. Now, I never once imagined that then I'm in a lodge, I look after people with a brain tumour.
Yeah.
What happens when reality projects itself upon you? Now, you're saying about the reality of, you know, taking the choice of reducing her,
I'm not criticizing her,
No,
or maybe it sounded like, maybe I did. I'm not criticizing her, it's just my person.
No, I'm not talking about that. What happens though when the reality, you know, you're saying about thinking, when it imposes itself upon you, when you bring something reverse?
Yeah. Well, then obviously is really up to you what you do with it, isn't it? We know, so, you know, I mean, again, luckily I am healthy, hopefully, you know, and I will be, but I think, you know, from what I'm talking to people and reading to people, and you know, people get ill, and then there's a big choice, what do they do then? Exactly, what do they do then? Do they say, oh, you know, what happened, you know, and all, I mean, again, like, I'm saying all these things, I'm really lucky, I've never had that. But we all have these issues, even if we're not ill. You know, if we're unemployed, we lost a job, if we owe a lot of money, we go through difficulties, isn't it? And there's always two things you can do. Either you say, you know, like that, and then, from my experience, when you're like that, then they keep on coming, the hammers, you know. But if you say, all right, you know, go on, you know, we carry on, and I personally think the outlook, well, you know, maybe I'm a bit spiritual, I guess. I think the way you feel has a huge impact on your experience in life. I'll give you an example, completely different, yeah, but so I was in the States, or in North America for a year. and I was hitchhiking for about 3-4 months. And I was just in the time of my life, you know, I was quite young, no girlfriend, no kids, you know, I didn't have to do anything. I just traveled around. And I met the most amazing people in the world I've ever met. And people were so friendly. I mean, for 3 or 4 months I was on the road. Okay? I had a tent, probably used it 10 days to sleep in my tent. All the rest of the time, you know, I spent it with people. And people opened their hearts. People were kind. You know, you hear a lot of stuff about America, and the people were so friendly. Okay? So, you know, it's very common for people to experience the same thing and have completely different experience, really. And I think that's a lot to do with where you see things. You know, you look at the empty glass or all that sort of stuff. But yeah, I think you wanted to ask.
Back to the
Yeah.
split experiment. But how do you explain the fact it goes through one slit or the other slit, or both slits, by the many worlds theory?
Yeah.
In that, in one world it goes through one slit, in another world it goes through another slit.
Yeah. I don't know
And
too
it's
much
only-
about it,
And it's only when the waveform collapses do
Yeah.
the multiple realities sort of
Yes.
fall down on themselves.
Yes. And this is another way of, I mean, everyone agrees on this experiment. There's a lot of debate, hot debate on the interpretation of these results. One is the many world theory, which I think we kind of know the same amount. I don't know more than you. Okay?
I dabble.
Yeah, the same here. I don't know too much. And that's one way of doing it. But then I'm thinking, is it more sane to think about many worlds, or just to think that things don't exist? I mean, I think it's as crazy. They're both equally crazy. You know, just go whatever happens. Yeah.
I'm just worried the ideas that you're giving Francis for her next book is going to change the whole reality of the world. I just wish she wasn't here now.
Tal, there was one right at the back on the right. No. Another question. The lady on the corner with the red shirt. Sorry.
Right, yeah.
Given all this, is it possible to say categorically that anything is impossible?
That anything is impossible. Yeah, I mean, yeah. Yeah, I'm just trying to think what I can say.
Honest politicians.
Or bankers.
Got you on that one.
No, I think what you is it now actually possible to say anything is
I don't think it's ever been possible to say that. It's just you will be stretching the limits of probability beyond their
Actually, I've got something to say on this. A couple of things. First of all, there's a really good book by, you know the name, we spoke about
Michio Kaku.
Michio Kaku, a physicist, American physicist, who's got Asian origin, and he does a lot of popular science. He's had one, the physics of the impossible. So he's got a book, and it's really interesting. I didn't read the whole of it, but he talks about impossible things, and he's got like different categories. So he says you've got the impossible things that, well, right now they're possible, but in the near future they'll be possible. Okay, and so these are like not very hardcore ones, yeah. And by one of those is teleportation. That's actually one of the things that we reckon we're going to get that soon. And then you've got the next stage, which is impossible, which is you know, impossible right now and probably in the near future, but you know, given 500,000 a year, you know, enough technology, this should be able to be possible. Okay, and I can't remember examples that he had there. And then he does have, and I didn't get to that stage, he said there are genuinely certain things that are impossible, and he said, you know, they will just never happen because we know these laws of physics. Now, I didn't read the whole book, but, you know, yeah, if things are not physical, really, then, yeah, that kind of does not allow for that last stage of completely impossible. So maybe I agree with you, I don't know. But maybe, I mean, yeah, who knows, you know, just according to this theory, these things here, they're not impossible. Once they were measured, once They went past where there was a given information that they are real, and then they have to obey certain laws. So after we measured, we know for a fact that these guys went through the slits, then they are real marbles, and we can't do magic with them, you know?
Yeah, but they're not, to begin with.
To begin with, they're not.
The laws
Yeah. Yeah, yeah, yeah. So maybe there is no, yeah. Which is quite a good art. That's good. Yeah.
If you look at it on a more galactic level, what you're saying there is, you know, if we can measure it in theory, there'll be these two lines on the board at the back. Now, in theory, that means there's another Earth somewhere matching the other one that's on the board at the back. Which one is reality?
Yeah.
Because according to that, both of them are.
Well, that's, I guess, the many world theory part, maybe interpretation. So for every certain result, a certain measurement that you've made, in another world, another universe, another result came. But I don't really know too much about that. And, yeah. But there is that many world theory, and I think that's what you understand, what you said is part of that understanding. And the reality, I don't know, there's one reality and maybe there's a bunch of us sitting in a room in a different world.
Good beginner's book on quantum physics called How to Teach Your Dog Quantum Physics. Unfortunately, my dog would never pay attention.
There's a very interesting guy.
Is it just the gentleman there? Yeah.
Getting back to what happens if you had a third slit? Does it change the dynamics?
Yeah.
Or does the wave pattern progress the same?
Well, from what I know, and we do that in high school, yeah, you can add one more slit, you can add another million slits, we do that. And there's still an interference pattern. So the interference pattern is slightly different in the sense that it's more sharp. We call it diffraction grating. So you've got little lines.
So basically, the more information gives you a more precise result.
Yeah.
But if you measure and know which always do you still get the same result?
From what I know, they didn't do this experiment with diffraction grating. I think probably difficulty will be in getting different kind of crystals, you know, to give you different results, because you need to figure out which slit it went through, and then you have to different.
Would the electrons still effectively go through all three slits then?
Yeah. I mean, what I'm told you now is just something we do in high school. So instead of 2 slits, you'll take 3 and 4. We show that, you know. Ask Gary, and he brings them. And then you get, the pattern you get is quite similar to that, it just becomes sharper. But they didn't, it's interesting, maybe that can shed some more light. To do this experiment with more than 1 slit. As far as I know, they haven't done it. It's something, an idea. Yeah.
Okay, ladies and gentlemen, I think we've explored the